The performance of distribution transformer cannot be determined by the commercial efficiency which we have studied in our previous videos. To determine the performance of distribution transformer, we have to use all-day efficiency. In this video, we will see what is all-day efficiency, and we will also solve numerical problems on all-day efficiency of transformer. We have studied that efficiency of a transformer is defined as the ratio of output power to input power, and therefore efficiency it is given as output power divided by input power multiplied by 100. Now this efficiency of transformer it is called as ordinary efficiency or commercial efficiency. Now this ordinary or commercial efficiency cannot be used to judge the performance of distribution transformer, because in case of distribution transformer the load on secondary side it is not constant, but this load varies at different hours of the day. For example, if the distribution transformer if it is mainly used for supplying lighting load and fan load, then the transformer may be lightly loaded in the morning. So in early morning period the load on transformer it is very low. The load may be also low during late night hours, whereas during evening the load will be maximum. But even if the load on transformer is very low, we have to keep the primary of distribution transformer energized. Means primary must be connected to rated supply even if the load on transformer is very low, and this primary is to be kept energized for all the 24 hours. Now we know that there are two losses in transformer, copper loss and iron loss. Copper loss depends on load on transformer, whereas iron loss is constant from no load to full load, and therefore in case of distribution transformer core loss will occur throughout the day. Means for all 24 hours core loss will occur, whereas copper loss will occur only when the transformer is loaded, and this copper loss it depends on the magnitude of load current. So in distribution transformer copper loss is variable, whereas core loss or iron loss it will occur throughout the day, that is for 24 hours. And therefore when we design the distribution transformer, so while designing such distribution transformers we have to take care that the core loss it must be minimum, otherwise it will affect the overall efficiency of transformer. So while designing distribution transformers care must be taken to keep the core losses to a minimum, and that is why in case of distribution transformer we cannot judge its performance by ordinary efficiency or commercial efficiency. But if you want to judge the performance of distribution transformer, then we have to use all day efficiency, or this efficiency it is also called as energy efficiency. So energy efficiency or all day efficiency is used to determine the performance of distribution transformer. We have seen that the load on distribution transformer is not constant, but it is variable, and therefore if you want to calculate the all day efficiency of distribution transformer, then you must know the load cycle of the transformer. Now the load cycle is nothing but the variation of load on transformer during a day or during a period of 24 hours. So if this data, that is how the load on transformer varies during a day or during a period of 24 hours, if it is available, you can calculate the all day efficiency. This all day efficiency of distribution transformer, it can be defined as the ratio of output in kWh, that is output in kilowatt hour, to the input in kilowatt hour. Again, during a period of 1 day, that is during a period of 24 hours. Now, in ordinary or commercial efficiency, we use output in kW or output in watt, whereas the input, it is also in kilowatt or in watt. But here, instead of kW, we are using kWh, that is kilowatt hour. Means here we have to consider the energy output of transformer in kWh, and similarly here we have to consider the energy input to the transformer, again during a period of 24 hours. And that's why this all day efficiency, it is also called as energy efficiency, because we have to consider the energy output and energy input to the transformer. And therefore, the all day efficiency, it can be written as energy output in kWh divided by energy input in kWh for a period of 24 hours. Of course, if you want the all day efficiency in percentage, this must be multiplied by 100. Now, you know that input is equal to output plus losses, and therefore all day efficiency can be written as energy output in kWh divided by energy output in kWh plus losses in kWh, again for a period of 24 hours. Now, there are two losses in transformer, iron loss and copper loss, and therefore we can write the expression for all day efficiency as all day efficiency, it is equal to energy output in kilowatt hour divided by energy output in kilowatt hour plus iron loss again in kilowatt hour and copper loss in kilowatt hour, and again this is for a period of 24 hours. And if we want percentage efficiency, this must be multiplied by 100. So, using this expression, we can determine the all day efficiency or energy efficiency of distribution transformer. Let us now solve example 1. A 100 kVA distribution transformer has full load copper loss and core loss of 1.5 kilowatt and 2 kilowatt respectively. So, here the given data is rated kVA of transformer, it is equal to 100. Then copper loss at full load WC, it is equal to 1.5 kilowatt, and core loss in transformer WI, it is given as 2 kilowatt. Calculate all day efficiency, means here you have to calculate efficiency all day. If during 24 hours in a day it is loaded as follows, means here load cycle of transformer, it is given. So, first time slot, it is 6 am to 10 am, there is half load. Then 10 am to 6 pm, there is 1/4 load. 6 pm to 10 pm, full load, and 10 pm to 6 am, there is no load. Now, assume load power factor as unity, means here you have to assume that cos phi is equal to 1 for all the loads. Now using this data, we have to calculate the all day efficiency, which is output in kWh divided by output in kWh plus iron loss in kWh plus copper loss in kWh. So we have to determine what is the output in kWh and what are the losses in kWh. So let us prepare one table for that. So first column, there is time slot. So what is the first time slot? It is 6 am to 10 am. So these are 4 hours. So second column is number of hours. So in the first case, number of hours are 4. Then next time slot, it is 10 am to 6 pm. So number of hours are 8. Then third slot, it is 6 pm to 10 pm and number of hours will be 4. And last slot, it is 10 pm to 6 am. So the number of hours again are 8. Now what is the output kVA of transformer? Now rating of transformer is 100. So we will get 100 kVA output when the transformer is fully loaded. But load is not constant. So during the first slot, what is the load on transformer? It is half load. So if there is half load, we take the percentage of loading X as 0.5 and output will be equal to 0.5 into 100, that is 50 kVA. So for the first time slot, the output kVA, that is X into kVA, it will be 0.5 into 100, that is 50 kVA. Now in the next time slot, there is 1/4 load. So in this case, X will be equal to 1 by 4, that is 0.25. So if X is equal to 0.25, output kVA will be 0.25 into 100. So it is equal to 25 kVA. Now in the next slot, that is 6 pm to 10 pm, there is full load on transformer. So in this case, percentage loading X will be equal to 1. So output kVA, it is 1 into 100, that is 100 kVA, because in this case the load on transformer is full load. And in the last slot, 10 pm to 6 am, there is no load. Means in this case, percentage loading X is equal to 0. So obviously if there is no load on transformer, output kVA will be equal to 0. So 0 into 100, that is 0 kVA. So this is the output kVA, but we need output in kilowatt. So we have to multiply this kVA by cos phi, so that we will get the output in kilowatt. So we have to obtain X kVA cos phi. X kVA is already calculated in this previous column. So we have to multiply this X kVA by cos phi. Now in this particular example, it is given that cos phi is equal to 1 for all the loads, and therefore we have to multiply this X kVA by 1 in all the cases, and therefore during first time slot, the output in kilowatt will be 50 into 1, that is 50 kilowatt. In the next slot, it will be 25 into 1, because cos phi is 1, so 25 kilowatt. During next slot, it is 100 into cos phi, so 100 into 1, that is 100 kilowatt. And in the last slot, the output is 0 kVA, and that's why output in kilowatt, it is also 0 into 1, that is 0 kilowatt. Now we need the output in kWh, means this output in kilowatt must be multiplied by number of hours. So output kilowatt multiplied by number of hours. So during first slot, total number of hours are 4. So output in kWh for first time slot, it will be equal to 50 into 4, which is equal to 200 kWh. Similarly, for next time slot, number of hours are 8 and output in kW it is 25. So output in kWh it is 25 into 8, which is 200 kilowatt hour. During next slot, output in kilowatt it is 100 and number of hours are 4. So 100 into 4 it is 400 kilowatt hour. And during last slot, the output in kilowatt is 0 and number of hours are 8. So 0 into 8 it is equal to 0. So this is the output in kilowatt hour during 24 hours. Now we have to calculate copper loss in kilowatt hour. So copper loss in kilowatt hour is loss in kilowatt multiplied by number of hours. So first of all, we have to calculate what is the copper loss in kilowatt during each time slot. So this copper loss in kilowatt, it can be calculated using copper loss is equal to X square WC. So here for first slot, X is equal to 0.5. So 0.5 square into WC. WC it is given as 1.5 kilowatt. So in the first slot it is 0.5 square into 1.5. If you solve this, it is 0.375. Then in next slot X is 0.25. So 0.25 square into WC, that is 1.5, it is 0.09375. Then during next slot X is equal to 1. So 1 square into 1.5, which is equal to 1.5 kilowatt. And in the last slot the transformer is not loaded, means X is equal to 0, and therefore copper loss is also equal to 0. So 0 square into 1.5, which is equal to 0. Now this copper loss in kilowatt, it must be multiplied by corresponding number of hours, so that we will get copper loss in kilowatt hour. So to calculate the copper loss in kilowatt hour, we will multiply this copper loss in kilowatt by corresponding number of hours. So in first slot number of hours are 4. So 0.375 into 4, which is 1.5 kWh. Then in the next slot it is 0.9375 into number of hours are 8. So it is 0.75. Then in third slot it is 1.5 into number of hours, that is 4, which is equal to 6 kWh. And in the last slot copper loss is 0 and number of hours are 8. So 0 into 8, it is equal to 0. Now using this we can calculate what is output kWh for 24 hours. So we have to add all these output kWh so that we will get total output in kWh for 24 hours. So total output in kWh, it is equal to 200 plus 200 plus 400. So if you add all these, you will get output in kilowatt hour during 24 hours as 800. Now similarly you can calculate total copper loss in kWh. So total copper loss in kWh, for this you have to add this 1.5, 0.75 and 6. So if you add this, you will get total copper loss in kilowatt hour, it is 8.25. So now you know the total output in kWh and total copper loss in kWh. Now we have to calculate total iron loss in kWh. So total iron loss in kWh, it is the iron loss multiplied by 24, because iron loss occurs during all 24 hours. So it is Wi into 24. Wi is given as 2 and number of hours are 24. So 2 into 24, which is equal to 48. So iron loss in kilowatt hour, it is 48. Now we can use the expression for all day efficiency and calculate the all day efficiency. So efficiency all day, it is energy output in kWh divided by energy output in kWh plus iron loss in kWh plus copper loss in kWh. Now we can substitute the values. Energy output in kWh, it is 800. So divided by 800 plus iron loss in kWh, it is 48, and plus copper loss in kWh. Now of course all this is for 24 hours. So plus copper loss in kWh, it is 8.25. So substituting the values, 800 upon 800 plus 48 plus 8.25 multiplied by 100. So all day efficiency, if you calculate this, it is 93.43%. Let us solve next example. A transformer has its maximum efficiency of 98% at 15 kVA at unity power factor. So it is given that the maximum efficiency of transformer, it is 0.98 or 98%, and the load kVA at maximum efficiency is equal to 15, and the power factor when efficiency is maximum is unity. That means power factor, it is equal to 1. During a day, it is loaded as follows. So load cycle is given. For first 12 hours, the load is 2 kilowatt and power factor is 0.8. During next 6 hours, the load is 12 kilowatt and power factor is 0.8. And during last 6 hours, the load is 18 kilowatt and power factor is 0.9. Find the all day efficiency. So here let us assume that maximum efficiency occurs at full load, and therefore full load kVA, it is equal to 15. Full load or rated kVA, it is equal to 15. Now from this rated kVA and maximum efficiency, we can determine the iron loss and copper loss. So first of all, the output power at maximum efficiency. So it is kVA into cos phi. So kVA is 15, cos phi is 1. So output power at maximum efficiency, it is 15 kilowatt. Now you know the expression for efficiency, which is output power divided by input power, and efficiency is maximum, which is equal to 0.98, and output power at maximum efficiency is 15 kilowatt. So from this you can calculate the input power when efficiency is maximum. So input power at maximum efficiency, it is output power, that is 15 kilowatt, divided by efficiency, that is 0.98, which is equal to 15.31 kilowatt. Now you know the relation between input and output. So input power, it is equal to output power plus losses, or losses is equal to input power minus output power. So input power is 15.31 kilowatt, output power is 15 kilowatt, so losses are 0.31 kilowatt. So this is iron loss plus copper loss. But when efficiency is maximum, both the losses are equal, and therefore iron loss and copper loss are equal, and these are equal to this 0.31 divided by 2, which is 0.155 kilowatt. Means both Wi and WC is copper loss at full load, both are equal to 0.155 kilowatt. So using this we have to calculate the all day efficiency, and for that again we will need output in kWh and losses in kWh. So again we will prepare one table. So first column, it is number of hours. So during first slot these are 12. Next during these 12 hours the load is 2 kilowatt. Then cos phi is 0.8. Then during next 6 hours load is 12 and cos phi is 0.8. During next 6 hours the load is 18 kilowatt and cos phi it is 0.9. Now we can calculate what is the load in kVA. So you know that kW it is kVA into cos phi. So kVA it is equal to kW upon cos phi. So load in kilowatt divided by cos phi. So in the first case it is 2 upon 0.8, which is 2.5. In the second case it is 12 upon 0.8, which is 15. And in the third case it is 18 upon 0.9, it is 20. So what will be the percentage of loading? So in the second case you can see the load is 15 kVA and rating of transformer is also 15 kVA. So in this case percentage of loading X will be equal to 1. Then what is the percentage of loading in other cases? So in the first case it will be 2.5 divided by 15. So it is 0.17. Means in the first case there is 17% load. During next slot X will be equal to 15 upon 15, that is 1, and in the next slot it is 20 upon 15, which is equal to 1.33. Means during this period the transformer is overloaded and it is 33% overloaded. Now we can calculate the output power in kilowatt. So it is output in kilowatt multiplied by number of hours. Now we know the number of hours, that is 12, 6 and 6, and we know the output or load in kilowatt, it is 2, 12 and 18. So we can calculate output in kilowatt multiplied by number of hours. So in the first case it is 12 into 2, that is 24. In the second case it is 12 into 6, that is 72, and in the third case it is 18 into 6, that is 108. So this is the output in kilowatt hour during various time slots. Now the copper loss in kWh. So copper loss in kWh, it is equal to x square Wc. So this is the copper loss in kilowatt multiplied by number of hours. So in the first time slot X is equal to 0.17. So 0.17 square into Wc. Wc is 0.155 into number of hours. In the first time slot number of hours are 12. So it is 0.17 square into 0.155 into 12, which is equal to 0.057. Then in the next time slot X is equal to 1. So 1 square into 0.155 into number of hours, these are 6. So it is equal to 0.93. And during the last slot the percentage of loading X is 1.33. So 1.33 square into Wc, that is 0.155 into number of hours, these are 6. So it is 1.645. Now we can determine the output in kWh for 24 hours by adding all these outputs in kWh. So total output in kWh, it is 24 plus 72 plus 108, which is 204 kilowatt hour, and total copper loss in kWh. So it is equal to addition of all the three copper losses in kWh. So it is equal to 2.632. So if you add 0.057, 0.93 and 1.645, you will get the total copper loss in kWh. It is 2.632. Let us now calculate the iron loss in 24 hours. So total iron loss in kWh in 24 hours, it is Wi into 24. Wi is 0.155 multiplied by 24, it is 3.72 kilowatt hour. Now we know the total copper loss in kilowatt hour, total iron loss in kilowatt hour, and total output in kilowatt hour. Using this, we can calculate the all day efficiency. So all day efficiency is total output, that is 204, divided by total output plus iron loss, that is 3.72, plus copper loss, that is 2.632, multiplied by 100. So solving this, we get all day efficiency as 96.98%. So in this way, you can determine the all day efficiency of transformer. But for that, you must know the load cycle of transformer. In this video, we have studied what is all day efficiency and solved numerical problems on all day efficiency. In our next video, we will see the another important performance indicator of transformer, that is voltage regulation of transformer. Thank you.